Hi everyone, again with Curved Mirrors. This is the second video about section 2 chapter 17 in our physics book. If you didn't watch the first video, watch it now, then watch this video. Today in this video we are going to talk about the equation of the spherical mirrors and the equation of the magnification. So by the end of this video you should be able to calculate the distances and the focal lengths using the mirror equation for convex and concave spherical mirrors. What are these two equations? Let's see. The first equation is the mirror equation. It states that, or the formula of it is 1 over f equals 1 over xo plus 1 over xi. Xo is the object distance, or the distance between the object and the mirror. It's positive when we are dealing with a real object that's placed in front of the mirror. It's going to be negative if we are dealing with a virtual object behind the mirror, which is not a common case in our problems. Xi, the image distance, again it's positive if the image is real and formed in front of the mirror. It will be negative if the image is virtual and formed behind the mirror. F, as you know, the focal length. It's positive with concave mirrors and negative with convex mirrors. So again, 1 over the focal length equals the sum of 1 over the object distance plus 1 over the image distance. The second equation is the magnification equation. M, which is magnification, equals hi divided by ho, which equals negative xi divided by xo. Hi, the image height, which is positive for virtual image and negative for real images. Ho is the object height, and it's always positive in all our problems. M, the magnification. M, always a number and a sign. It's represented by positive 2, negative 3, positive half, negative quarter, and something like that. So we have to separate between the sign and the number or the digit next to it. For the signs, positive means virtual image, negative means real image. So if the magnification is positive, we are dealing with a virtual image. If the magnification is negative, we are dealing with a real image, or the image is real. Okay? Now, let's go to the number. If the number is more than 1, whatever the sign is, we are not talking about positive and negative. We are talking about the digit itself. If the number is more than 1, so the image is larger than the object. If the magnification is less than 1, so the image is smaller than the object. If the magnification is 1, so the image has the same size as the object. So we are going to deal with these two equations, and we use them to solve the problems like this one. Example problem 2, which is in page 476. A concave mirror has a radius of curvature of 20 centimeters. You place a 2 centimeter tall object 30 centimeters away from the mirror. What are the image position and the image height? So we have 20 centimeters radius of the curvature R, and the height of the object is 2 centimeters, and the object distance is 30 centimeters. We are looking for the image position and the image height. So the given are R equals 20 centimeters, HO equals 2 centimeters, XO equals 30 centimeters, and the unknown are HI and XI. If we draw a ray diagram for this problem, remember that XO is the object distance, which is 30 centimeters, greater than the 20 centimeters, which is the radius of curvature. So if we use the ray diagram, the object should be at a distance greater than C. By drawing the 3 rays, or 2 only, it doesn't matter. So the image will be, as you see here, it's upside down, which means inverted, smaller than the object, and between C and F. And of course real, because it formed in front of the mirror. Let's use the equation to solve this one. First, the focal length equals the radius of curvature divided by 2, so 20 divided by 2 equals 10 centimeters. If we substitute the numbers we have in the equation of the mirror, 1 over f equals 1 over xo plus 1 over xi, so 1 over 10 centimeters, which is the focal length, equals 1 over 30, which is the object distance, plus 1 over xi, which is the image distance. So xi will equal 15 centimeters by calculations. Whenever the image distance is positive, so we have a real image and in front of the mirror. Now we are looking for the height. We will use the magnification equation. Magnification equation, m equals hi over ho equals negative xi over xo. So we're going to use these two terms. Hi over ho equals negative xi divided by xo only. So hi over ho, which is 2 centimeters, equals negative, from the formula, xi, which is 15 centimeters, divided by xo, which is 30. So hi equals negative 1 centimeters. Negative 1 centimeters means that the object is inverted, upside down, as you see here, and is smaller than the object. And this is how to solve a problem of a concave mirror by the equation of mirror and the equation of magnification. Now, what will happen if we use a convex mirror? It's going to be the same procedure. Let's see. Example problem 3, page 480 in your book. A convex security mirror has a negative 0.50 meter focal length. A 2 meter tall forklift is 5 meters away from the mirror. What are the image position and the image height? So again, the given are f negative 0.50 meters. Of course it's a negative because the mirror is convex mirror. Okay, and the height of the object is 2 meters and the object distance is 5 meters, and we are looking for hi and xi. Now if we draw the ray diagram like this, it doesn't matter where the object is in convex mirror. If you remember from the previous video, we say that it doesn't matter where the object is, as long as it's in front of the convex mirror. Always the image will be smaller than the object and virtual behind the mirror, and upright, of course. As long as it's virtual, it's going to be upright. If it's real, it will be inverted. Okay, now let's solve using the equation. 1 over f equals 1 over xo plus 1 over xi. Now I got the f, not like the previous problem. So f equals negative 0.5 here, xo is 5 meters, plus 1 over xi, which is an unknown. Xi equals negative 0.45 meters. So the image distance is negative, which means it's behind the mirror. And as long as it's behind the mirror, the image is virtual image, not real image. What about the height? Let's use the magnification equation. And we are going to take this part only. Hi over ho equals negative xi over xo. Hi, which is an unknown, ho 2 meters, sorry, negative is here. Xi, which is negative 0.45, I know negative times negative is positive, divided by xo, which is 5 meters. Cross multiplication, hi equals 0.18 centimeters, which means it's an upright and smaller than the image. Upright because it's positive and smaller than the object. Yeah, the image is smaller because it's less than 1. One thing you need to put in your mind, that the unit must be the same. It doesn't matter if all of them are centimeters or all of them are meters or millimeters or kilometers. It doesn't matter as long as they are the same. So you don't need to convert anything. If one of them is centimeters and the other one is meter, you need to convert one of them to be all the same. Okay, so we're not working with SI units here. We use it if they are all meters, do your job. If they are all centimeters, do your job. It doesn't matter. Okay, that's it. For more practice, you need to solve problems from 13 to 17 about concave mirrors, page 479, and problems from 18 to 22, they are about convex mirrors, on page 480. And for more explanation, join our Classera's virtual classroom tomorrow Monday, from 11:40 to 12:10. And if you have any more questions, write them in a comment in Coursera discussion room. That's all. Thank you.